Hello students, welcome back to JCE Connect series of lectures. So in previous uh, lectures we were discussing about the velocity triangle and how to construct a velocity triangle and all. So let us continue with the same here in this particular lecture. So here we'll discuss how to construct a velocity triangle and all. So here in this particular figure, so this figure represents a jet of water striking moving curved plate. So the jet is coming out of the nozzle and it is striking the moving curved plate or the vane tangential to the uh, shaft. We can call it tangential to the shaft of the turbine, like this. This is the turbine, and if you take the perpendicular to this, if you take this perpendicular to the shaft, that represents the axis of the turbine, and it is striking in this direction, means this will be the tangential direction, tangential to the shaft. So the jet is striking tangentially at one of the tips. As the jet strikes tangentially, then the loss of energy due to impact, of the jet will be taken 0. And in this case, as the plate is also moving, the velocity with which the jet of water strikes is equal to the relative velocity. The velocity with which the jet of water strikes is equal to the relative velocity, and relative velocity of the jet then with respect to the plate. Also, the plate is moving in different directions. This plate is moving in different directions of the jet. Then the relative velocity at inlet will be equal to the vector difference of the velocity of the jet and the velocity of the plate. So this, the relative velocity to be taken, the vector difference of the velocity of the jet and the velocity of the vane. And as we know the addition of vectors, how the vectors can be adding. See, the addition of vectors, as we were discussing previously, so that is a triangle rule for the addition. That is head to tail, you can call it as a head to tail. Here we take head to tail. Since the jet is striking in this direction like this with a velocity v1, and the vane is moving in this direction with a magnitude u1. Jet velocity is v1 and the vane velocity is u1. So we are taking the vector difference for the relative velocity. So as we know the definition of vector, the vector will be having both magnitude as well as the direction. So here the arrow represents the head, this represents the head, and this represents the tail. Then how to add these two vectors? Just you join the tail of first vector to the head of next vector. So this gives you what? VR1. Then the resultant is what here? The resultant is V1, that is U1 bar plus VR1 bar. Then if you want VR1 vector is equal to V1 vector minus U1 vector. Then instead of keeping this vector here, if you shift that vector, this is giving a magnitude and direction v1, and this vector you just shift and keep here, see the same magnitude, this will be u1, then the join these two, this will be vr1. Okay, so this can be drawn at the inlet of the blade here. Now same way of followed here and the drawn. As we know, the jet of water is coming out of the nozzle with a velocity v1. Okay, so then the blade is moving with a velocity u. Since we are drawing the triangle at inlet, so let us take the velocity at the inlet tip. This is the inlet tip and this will be the outlet tip. And this vane is moving as I explained earlier how it moves. Okay, and this velocity is been taking u here. And these jet as well as the vane both are having direction as well as a magnitude. And let us shift this vector and keep here with the same magnitude and direction we have shown here, that is u1. Then the difference of these two will be the VR1. With this velocity the jet is entering into the blade passage, and we have assumed the blade passage is very smooth. There is no any frictional loss here, and whatever velocity with which the jet entering into the blade passage, it will glide over the surface and exit with the same velocity, and it is mentioned here at the outlet that VR2. Okay, if there is no loss in the blade passage, then VR1 is equal to VR2. If any losses, then VR1 is not equal to VR2. Then how to draw the inlet velocity triangle, and it will be having a various components, and from the inlet velocity triangle finally we have to calculate the force exerting by the jet on the vane as well as the work done by the jet. So you look at the inlet velocity triangle, the various components are being drawn, and let us understand one by one and way to also understand the construction of velocity triangle. Now how to construct this velocity triangle? As we know, the jet is coming with a velocity v1 and it is hitting the blade, and the blade will be moving with a velocity u. Then the difference of the two to be taken as relative velocity, and these three components typically represents what? The velocity triangle. By having these three components we can construct the velocity triangle, that is v1, vr1 and u1, that is blade velocity. So let us look at the inlet velocity triangle. Take a point A and draw a line AB, and you mark a B on the tip of the blade. Take point A and draw a line AB and B to be taken at the tip of the vane. And this AB line should be having a magnitude of V1. And this AB is equal to V1. And this will be having both magnitude as well as direction. And this V1 will be making an angle of alpha with the horizontal line. Okay, this V1 first you have to draw that V1 is equal to AB. Then the AB line, that is AB is equal to V1, and V1 making an angle of alpha, and this alpha is called as nozzle angle, or the angle between the direction of the jet and the direction of the jet and the direction of motion of the plate, and this is also called as a guide blade angle or nozzle angle, this alpha. The next, draw a line AC. As I said, this vane is moving in this direction, then we have shifted this vector and kept here, that is we have kept the tail of the plate vector to the joined the tail of the plate vector to the tail of the absolute velocity. Okay, so we kept here the same magnitude and direction. Draw a line AC, the mark here AC, and join C to B, that is draw a line AC, and that AC is equal to magnitude U1, and join C to B, and CB represents the relative velocity. CB represents the relative velocity, that is VR1 of the jet, that is at inlet. If the loss of energy at inlet, due to impact is 0, then the CB must be tangential direction to the vane at inlet. This CB must be tangential direction to the inlet. Just to extend and draw tangential to the vane and join for the horizontal line, and this angle represents theta. Then this theta is angle made by the relative velocity with horizontal. Alpha is angle made by the absolute velocity with horizontal, and theta is angle made by the relative velocity with horizontal. Then next, from B, draw perpendicular BD. From B, draw perpendicular BD meeting the horizontal line AC. This horizontal line AC, this you have to draw a perpendicular line from B, and that line should meet the horizontal line AC. Then produced at D, then BD represents the velocity of flow, VF1, the velocity of flow VF1. Then AD represents the velocity of whirl at inlet. This is VW1. This is called whirl velocity VW1, and this is velocity of flow, that is the flow velocity at inlet, VF1. Then angle BCD is theta, that is vane angle at inlet. This angle equal to this angle and this angle. Okay, now this VW1 is a whirl velocity at inlet, and because of this velocity this vane gets rotary motion, and because of this velocity the fluid enters into the blade passage. This is called a flow velocity, and VW1 is nothing but the component of V1. VW1 is a component of V1, that is nothing but V1 cos alpha. So look at this figure. I written here VW1 is V1 cos alpha, that is component of V1. So this V1 is making an angle of alpha. So VW1 is nothing but the whirl velocity. Whirl means rotary motion. Then VW1 and VF1 are the components of V1 in horizontal direction as well as perpendicular direction. So VW1 is V1 cos alpha and VF1 is V1 sin alpha. This V1 is been resolved into two components. So that is one in perpendicular direction and one in horizontal direction, like this. This V1, if you want to resolve, you will get one component perpendicular like this, and other you get horizontal. The same we are just shifted here and drawn here, one horizontal and one perpendicular. So we have got VW1, that is V1 cos alpha, and VF1 as V1 sin alpha. This triangle, what it represents, inlet velocity triangle completely. Okay, so try to understand this one. So initially we have to draw V1, then we have to draw U1, then join, that is draw a line CB joining that is C to B, that represents VR1. Then the resolve this V1 in horizontal as well as a vertical. The horizontal component represents the whirl velocity VW, that is V1 cos alpha. The vertical component represents the flow velocity, that is V1 sin alpha. And this VR1 making an angle of theta, that is a vane angle at inlet, and alpha is called as a nozzle angle or the guide blade angle. So this triangle ABD represents the inlet velocity triangle. I hope you understood this one. Similarly, draw outlet velocity triangle. Then as the jet enters the blade passage, it will not enter with this velocity, that is with absolute velocity, it will enter with relative velocity VR1. then it glides over the surface, then it exits with a velocity Vr2. Then how to draw the outlet velocity triangle? If vane surface is very smooth, if you are assuming this is a smooth, if there is no losses at all here, then the energy loss due to friction will be 0 here. Thus Vr1 is equal to Vr2. Whatever velocity with which the jet is entering, here the jet is entering with Vr1, with the same velocity it comes out. Hence Vr1 is equal to Vr2. Because we have assumed this vane surface is very smooth. If there is a loss due to impact or there is any frictional loss here, then this Vr1 is not equal to Vr2. These two will be of different velocities. Since here we are assuming this surface is smooth and there is no loss at all here, hence Vr1 is equal to Vr2. And Vr2 will be in a tangential direction. Again, this Vr2, the relative velocity will be in the tangential direction to the vane at outlet. So tangential direction to the vane at outlet. Then how to draw this velocity triangle at outlet? This triangle represents at outlet velocity triangle. Draw a line easy. So mark this tip. This tip is outlet tip. This is inlet tip. This is outlet tip. Water will enter in this like this. Then it exit like this. So where the water is entering inside the passage, that is called the inlet tip. Where the water is exit, that is called outlet tip. So mark a point E here, then draw a line EG in the tangential direction of the vane, in this direction, in the tangential direction of the vane at outlet, and cut this line by a magnitude of Vr2. Okay, draw this line EG, then cut this line by a magnitude Vr2. Then from G, draw a line GF like this. Draw a line GF from this point. Draw a line GF. Here I have marked as a F. Here I have marked as a F. In the direction of the vane at outlet. In the direction of the vane at outlet, and is equal to U2. This one is equal to U2. This also having a velocity at outlet. So here, look at this one, this figure. So this is the inlet tip where this blade is receiving the jet force here, inlet tip. When it moves along, when it starts moving, this also starts moving. Okay, when it rotates, both tip will start rotating, inlet tip as well as outlet tip. Okay, so this is the direction of vane, and draw a GF of magnitude U2. And the velocity of the vane, and this U2 represents the velocity of the vane at outlet. Join EF, then you join EF from E to F, you have to join, and that represents the velocity of the jet. When you join EF, this represents the velocity of the jet V2 at outlet, and it is having a magnitude and a direction both, that is V2. Then from E, again from E, draw a perpendicular line. You have to draw a perpendicular line from E to meet the line GF. You just extend this line and draw a perpendicular line from E to meet the line GF produced at H. So this from E you have to draw perpendicular up to the line GF, and which is produced at H. Then EH and FH, represents the velocity of flow, that is a Vf2 represents the velocity of flow and the velocity of whirl at outlet respectively. Again, this Vf2 and Vw2, they are nothing but the component of velocity 2 at outlet V2, it will be having a beta angle made by V2 with horizontal is a beta. Then VW2 will be V2 cos beta and VF2 is a V2 sin beta. So VF2 represents the velocity of flow at outlet and VW2 represents the velocity of whirl, that is the rotational velocity at outlet. Then angle pi, see here angle pi, it is marked here, it is angle made by the relative velocity at outlet, and that is called vane angle at outlet. And the beta represents angle made by V2 with the direction of motion of vane at outlet. That is angle made by the V2 with the direction of vane at outlet. And pi is called as vane angle at outlet. And the triangle EGH represents the velocity triangle at outlet. Okay, I hope you understood these triangles. So with these triangles, now we have to derive the equation, that is force exerting by the jet on the vane. So considering these two triangles, inlet as well as outlet. So here the pi is marked, that is a vane angle at outlet, and this is beta, and this angle we get, that is opposite angles what we get here, and this also beta, and this angle what we get, beta minus pi, beta minus pi. Okay, so I hope you understood this triangle. So this is very important, this triangle. So beta minus pi, where I mark, just look at that figure. Then I marked a beta angle. Beta is the angle made by V2 with the direction of motion of vane, and the pi is the angle made by the relative velocity at outlet with the horizontal. Okay, so here Vf2 represents the velocity of flow at outlet, Vw2 velocity of whirl at outlet. Okay, so here I have written V1 is the absolute velocity of jet at inlet, U1 is the velocity of the plate at inlet, Vr1 is the relative velocity of jet with respect to the plate at inlet, alpha is the angle between the direction of jet, this is for inlet velocity triangle, and the direction of motion of the plate, also called the guide blade angle or the nozzle angle, and the theta represents the angle made by the relative velocity Vr1 with the direction of motion of the plate at inlet, also called vane angle at inlet. Then Vw1 and Vf1, the components of absolute velocity of jet V1 in the direction of motion and perpendicular to the direction of motion of vane respectively. And similarly Vw1 is nothing but V1 cos alpha. It is also known as velocity of whirl at inlet acting tangential to the shaft or to the shaft axis, that is tangential components of the absolute velocity at inlet. Then Vf1 is V1 sin alpha. It is also known as velocity of flow at inlet, and that component is axial component of absolute velocity at inlet acting in the direction of axis of the shaft. Similarly, outlet velocity triangle, V2 represents the velocity of jet leaving the vane or absolute velocity of the jet at outlet of the vane. Then U2 is the velocity of the vane at outlet. Vr2 represents the relative velocity of jet with respect to the vane at outlet. The beta represents the angle made by the velocity V2 with the direction of motion of vane at outlet. And the pi represents angle made by the relative velocity Vr2 with the direction of motion of vane at outlet, and also the called vane angle at outlet. Then Vw2 and Vf2, the component of velocity V2 in the direction of motion of vane and perpendicular to the direction of motion of vane at outlet. And Vw2 can be taken V2 cos beta. It is also called as the velocity of whirl at outlet. And Vf2 is V2 sin beta. It is also called velocity of flow at outlet. The triangles ABD and EGH, that is this triangle ABD, triangle ABD and EGH, are called as velocity triangles at inlet as well as at outlet. Hence, these two velocity triangles are used to find the force experienced by the jet and work done by the jet. So further, next we have to derive the equation by utilizing the velocity triangle at inlet as well as at outlet. So the construction of velocity triangle is very important here. So typically it consists of absolute velocity, vane velocity and relative velocity. So once we construct with these three components, then next will be the resolution. You have to resolve the absolute velocity at inlet as well as at outlet, then you will be getting the components finally. So you will be getting the once you resolve the absolute velocity, you will be getting VW1 and VF1 at inlet, that is velocity of whirl as well as velocity of flow. Similarly at outlet also you have to resolve, you will be getting VW2 and VF2. They are called as a velocity of whirl at outlet, velocity of flow at outlet. Then once we know these all things, so then we can easily get the force exerting by the jet on the vane and work done by the jet on the vane. So with this concept of velocity triangle, I hope you understood this concept. Try to understand and just practice to draw the velocity triangle, how to draw the velocity triangle and all. Practice it and understand this one. Okay, so in the next part of this lecture again I'll be deriving the equation, that is Fx and work done by the jet and efficiencies. Okay, thank you.